For this example, I'm going to show you how to use the multiple regression dialog in JUMP. And I would just note that the version of JUMP that I'm using here, you can see is version 12. If you have version 11, there are some aspects of the dialog that are slightly different, but I'll point those out as we go along. The data set I'm looking at is called CARS-04. It contains fuel economy on a set of vehicles measured in 2004, and we have a set of potential predictor variables that we're going to have a quick look at. For example, the weight of the car, the horsepower, and so on. Each row represents a car in this data set. There's always also a context where we're interested in predicting the fuel economy of a car that is yet to be built. That's entered in the bottom row of the spreadsheet. We know it's going to weigh 4,000 pounds, have 200 horsepower, and those are the features we've specified, and we're going to use the multiple regression model to predict the fuel economy of this vehicle. Now, in this data set, it is the case that there are a couple of hybrids which are really not from the population of interest, and I can find those very quickly just by going through the distribution and having a look at the fuel economy. And I note that there are 2 points up here. These are both hybrid vehicles, and they don't really belong in the data set, and so I'm going to remove those 2 points before I get started with the regression modeling. Now, there's a number of ways of removing them. What I'm going to do is simply use the lasso tool, and then I capture the points. They're now highlighted, and I simply do a rows hide and exclude, and those points will have been removed from the analysis now. Remember, the point of this example is to have a look at multiple regression. So the multiple regression dialog goes from the Analyze menu, and you want to do Fit Model. The first thing to do is choose the outcome variable, and we've decided here to model not miles per gallon, but gallons per 100 miles in the city. So that's going to be the Y variable, and the two predictors that I'll look at are weight and horsepower. So I select those two variables and I add them in to the model effects. So here's the Y variable, fuel economy, and here are our two X variables that we're looking at, weight and horsepower. Now, sometimes it's useful if one's going to continue the modeling exercise to click on Keep Dialog Open, because then when we run this regression model, this dialog will remain open and we can go back to it and tweak the model if we so choose. So I've now got the multiple regression set up, and I simply have to click Run. When I do that, I get a whole set of output, and I'll discuss some of it right now. I won't discuss the effect summaries. I'll quickly run through the plots. This first one up here that I'm looking at is a plot of the actual fuel economy against the predicted fuel economy, and it's an overall graphic that gives you a sense of the predictive quality of the model. If the model were predicting perfectly, the points here would lie along this 45-degree line, and the extent to which they're close to that line gives you a sense of the quality of the prediction. Down here in the summary of fit, we have the usual suspects. Our main summaries that we focus on are R squared here at 0.8379. I'd call that 84%. I'd say 84% of the variation in fuel economy is explained by weight and horsepower. And the other number I'd be interested in looking at would be the root mean squared error, which is about 0.41 here. And what that allows me to know is that if I were to use this model for prediction within the range of the data, my 95% prediction was going to have a width of approximately plus or minus twice the root mean squared error. In other words, plus or minus 0.82 of a gallon. So that's the degree of precision that I can have when I use the model in this forecasting or prediction sense. The next bit of output I'll draw your attention to is the analysis of variance table. If you recall, this is sometimes known as the whole model test. I often refer to it as the gatekeeper test, and it's telling you, taken as a bundle, do the variables that have been offered to the model provide significant predictive power? And all that you have to do to answer that question is have a look at the p-value there, and it's highly statistically significant, less than 0.05. So we can say, yes, there is predictive power offered by the model. Note, though, it doesn't tell you which variables are important. It just says there's some value in these variables when viewed as a bundle. Now, before getting too caught up in any of these hypothesis tests, you do need to think about the underlying assumptions behind the regression, and I'll quickly show you where we can start to get a handle on that down here in the residual plot. And so this would be standard operating procedure whenever you run a multiple regression to have a look at the residual plot. And what you're hoping to see is basically no structure, because the residuals are encoding the noise in the system. And in this plot, I really don't see much structure, which is good. I certainly don't see heteroscedasticity, the non-constant variance. I don't see a systematic lack of fit, which would be evidenced by some curvature in the plot. I do notice an artifact, and that is a banding of the points. If you notice from top left to bottom right, that is an artifact. It just is being driven by the fact that the fuel economy variable is discrete. When EPA measures the fuel economy, it's measuring it in whole numbers, and that just propagates through the analysis into the residual plot, ultimately where you see this banding. So it's not really that interesting. In practice, one of the things I would be very interested in doing is identifying the points with the largest residuals and trying to explain them. Now, that explanation is certainly not a statistical skill. One would need to know something about cars in order to provide a reasonable explanation. But in terms of process, drilling down on the big residuals and trying to understand or explain them is a very useful thing to do. Continuing our look through the output, the next thing I'm interested in are the parameter estimates here, which are telling us the partial regression slopes, particularly for weight and horsepower. We can see them there. We can see standard errors, which is going to allow us to do some hypothesis testing through the t ratio and the p-value. And both of these are statistically significant, which tells us that in the presence of the other one, each one still adds significant predictive power to the model. So focusing on the weight one, I would say that in the presence of horsepower, weight adds significant predictive power. And likewise, on the horsepower one, within the presence of weight, horsepower is still able to add significant predictive power to the model. One of the things that we often do with this parameter estimates table is provide for ourselves a confidence interval, and you can do that by going into the table, right-clicking, going to columns, lower 95%, right-clicking columns, upper 95%, and now you can see the two ends of the confidence interval for these partial regression slopes. Final thing that I might do with the parameter estimates table is do the columns and the VIF. If you recall, that stands for variance inflation factor. It tells you about the collinearity between the two variables. And here the VIFs are only about 1.68, which really is not by most standards a high VIF. Yes, there is some correlation between these two variables. A VIF of 1 says no correlation between them, but it's not severe collinearity. Continuing looking through the output, the next thing I'm going to have a look at are the leverage plots. So you get one leverage plot for each variable that has been included in the model. The weight leverage plot here shows me the partial regression coefficient for weight. So one way of understanding this is that you're looking at the direct effect of weight on fuel economy after having taken into account horsepower. And really what you're hoping to see is some approximate linearity in the plot. And that says, yes, fitting a plane through this data made sense. And I do in this case. So both of these leverage plots are encouraging. They're not suggesting that there are any systematic problems with the model. Sorts of things that one would be interested in looking for in a leverage plot would be things like heteroscedasticity. Obviously, leveraged data points could be identified, and through their construction, you do get to see the residuals. The distance from the point to the red line is the residual from the multiple regression model. So you can pick out the big residuals. But their role is really the equivalent of a scatter plot in simple regression. They're very useful diagnostics for determining whether or not it was a rational thing to fit a linear model. In other words, you're hoping that points show approximate linearity, and you use them to diagnose problems with the regression, just as you would in a simple regression. Now, in terms of saving features from this multiple regression model, the two most common things that we're going to save are the residuals and the predictions. And the way you do that is right-click on the title bar, you go to Save Columns, and if you do Prediction Formula, let's do that one, right-click again, Save Columns and Residuals. I'll quickly go back into the spreadsheet now and show you what has appeared at the end of the spreadsheet. Two columns, there's the predicted value of fuel economy and there's the residual from the regression model. So you can drill down on the residuals, but here I'm interested in the prediction from this multiple regression for the car that weighs 4,000 pounds and has 200 horsepower, and it tells me that we expect to put 5.646 gallons in the tank to make sure this vehicle can go 100 miles. Now, by saving the prediction formula, if you go back into the spreadsheet, notice that there's a little plus sign over here on prediction formula. That means that the formula is stored in JUMP. If I just double click on that, I can see directly what the prediction formula looks like, and that can be quite helpful as the model gets more complicated. Now, typically, we don't just want to do a prediction, we would like to do a prediction interval. And the way that I'm going to get the prediction interval out of this output is to right-click on the title bar again, Save Columns, and what you want is InDiv confidence interval. And if I save that one into the spreadsheet, what you're going to see are two new columns at the end. And if I focus on the last row, can you see 4.83 to 6.45, 6.46 after some rounding. This is my 95% prediction interval for the amount of gas I need to put into the tank of this car to make sure I can go 100 miles driving in the city. The width of this prediction interval is approximately plus or minus twice the root mean squared error. So that's the basic output that one is going to look at from the multiple regression model.